Okay, good morning or afternoon, ladies and gents. So, first lesson of week 2 and the fifth style of lesson we're going to go to with trigonometric solutions and functions. For today, we're going to be basing on rational functions. Effectively, guys, what we're aiming to do today is understanding how to sketch a rational function. Now, guys, one thing I just want you to recall from the basic junior mathematics, a rational function can be put as a fraction, a over b. So effectively, guys, that's what we're aiming to do. So a rational function is the quotient of two polynomial functions, with the rule being f of x, our rational, must be p of x over q of x, where q of x, or our quotient, cannot equal 0. For this, you need to recall the information from our absolute values and our reciprocals here, because our aim is to sketch it all out. So for example 1, sketch the function 4 over x squared plus 3x minus 4. So first thing what we need to do, we need to factorize our denominator, which is the best part of this example here. What adds to make positive 3, but multiplies to make negative 4, positive 4, negative 1. So our denominator can get turned into x plus 4, x take 1. So what we can now do is graph the quotients. Because it has to form some form of parabola, and because of where it needs to be going through, it must cut the x-axis at negative 4 and positive 1. And of course, guys, if we want to find out a few things as well, which we need to, first up, to determine our minimal, so our turning point for x, we need to do something called the derivative. We haven't done this for any specialist, but I'd like to hope by now you've done a little bit of this for methods so far. So if q of x is equals x squared take 3x plus 3x take away 4, then its derivative must be 2x plus 3. Therefore, when y equals 0, for our derivative, x must equal negative 3 over 2. And of course, because that's our x component, we substitute this into our y component, and it gives us y equals negative 25 over 4. So our turning point, or our minimum, x is going to be equal to negative 3 on 2, y is equal to negative 25 on 4. If there's anything you can't follow, please pause and just read it all there. But that's not the only part of it, because obviously that is just drawing our actual quotient function. We need to note a couple of things. There will be vertical asymptotes at negative 4 and positive 1, and the x-axis will have a horizontal asymptote. So we'll just have a look back up here. We've already talked about absolute values showing reflections. We've also outlined reciprocals, which of course would link in over here. So it makes sense that there would be 3 extra components for this sketch. So to actually sketch out our lovely graph, we need to remember where the reflection is. So it's where the vertical asymptotes come from. To determine the y-intercept of our vertical asymptote, substitute x equals 0, gives us negative 1 over 4. Therefore, our y-intercept is at 0, negative 1 over 4. The follow-on point we need to do is figure out the maximum for this one here. So effectively, it should be a reflection of our y value, which is exactly what it is. The maximum is sitting at negative 3 on 2, because it must share the same components, but we just flip it around. Instead of being negative 25 on 4, it'll be negative 4 on 25. And lastly, guys, because the numerator for our function is 4, the graph gets stretched by a factor of 4. So you'll note over here that for our reflection, it doesn't just go a perfect little loop like our actual parabola does. It goes up and around. This type of work's time consuming, guys. And you're going to see, obviously, there's a page and a half just to get one thing. Let's see if we can make another one work. Example 2. Sketch the graph for y equals 2x take 1 over x plus 1. The first thing we can do, guys, is rewrite this function. So it becomes negative 3 over x plus 1 plus 2. First up here, guys, we need to draw a couple of different things. The first thing, we're going to determine our intercept for this one. So if y equals 0, we can rearrange it to figure out that x equals, I'll just bring this up a little bit here, x equals negative a half. Oh, sorry, positive half. So this is where our x-intercept is here. If x equals 0, our y-intercept will be a little bit further down. So we know that for x plus 1, it would have to effectively cut through over here somewhere. This isn't our endpoint. Oh, maybe it is, sorry about that. And of course, guys, because we're showing a reflection on this, we dried up our reflection over here. My apologies, guys, got caught up on our next question here. Please have a pause and jump on to the next one. Third example, sketch the graph y equals x over x squared take 4. First up, guys, like we discussed, if we can, rearrange our quotient so it becomes in its factorized form. In this case, x plus 2, x take 2. So we know that when we draw up this graph, we're going to have points over here. Because our numerator is less than the denominator, the horizontal component of the asymptote that we will be making is at y equals 0. So this is something we need to remember here. You're going to see the drawing a bit further down. For the vertical asymptote, the approach to x must be at plus or minus 2. So we know this because of how we factorize it. For our formula, to try and figure this out, we've already done this in a previous video here. Y equals plus or minus 1. So if x equals 0, if y equals 0, we can rearrange this to give us x equals plus or minus 2. And since our vertical asymptotes, I'll just read this a little bit further down before I show you my drawing. Since the vertical asymptotes occur when they both respectively approach negative 2 or 2, and because they are reflections of the original, we can plot them. So this turns into this. Our actual vertical asymptote and its reflection. The next thing, guys, before we show our fourth and final example, it can also be possible for rational functions to have oblique asymptotes. So this just means they're slanted. This occurs when the numerator has one more degree than the denominator. So what this means, if your denominator goes x squared, something ax squared plus bx squared, bx plus c, your numerator might look like ax cubed plus bx squared plus cx plus d, so an extra degree to it. To rearrange this equation, excuse me, you can either calculate it or use long division. Guys, I'm going to give you the hint. Use the calculator. You've got the graphics calculator, and I'm telling you right now, more often than not, the question will expect you just to write the rearrangement down from your graphics calculator than you would showing the long division. So let's get into our last example. Sketch the graph y equals x squared over x take 2. Now, if we wanted to rearrange this, and you can see I've done our long division for it here, we can rearrange this rational function into the form y equals x plus 2 plus 4 over x take 2. The slant asymptote just down here will effectively be the denominator. So the first thing, guys, we plot y equals x take 2, as we do here. So this is our first part. Because the numerator has a degree more than the denominator, it must have an oblique asymptote. So this is our component up here. We have a reflection, and it goes back around here. Sorry, we have our asymptote coming across, but it slants going along x take 2 until eventually it starts approaching. Also, because there is a reflection, it would have to occur in the opposite direction as well. Guys, this type of work's a little bit more tricky, so have a pause, go through my notes and Mr. Russell's, and try out those questions. All right, guys, good luck to you all, and I'll see you in the next one.